Good morning, one and all. So I'm going to handle the subject unconventional machining process, and especially in unconventional machining process, I'm going to take the topic abrasive water jet machining. I'm Arun, Kumar, assistant professor, mechanical department of engineering. Let's we go to the session. So abrasive water jet machining. Okay, so this is the schematic diagram of abrasive water jet machining. So before that, we are going to study some of the introduction about the abrasive water jet machining and the working principle. So abrasive jet machining, abrasive flow machining, and ultrasonic machining are the processes which are using abrasives for machining of materials. So in abrasive jet machining, air-driven abrasive jet strikes the workpiece and remove the material, while in ultrasonic machining, abrasive grains in liquid slurry strike the workpiece surface at ultrasonic frequency and cut the material at lower material removal rate. So recent developments have witnessed improvements in jet cutting technology by using abrasive water jet, where water is used as a carrier fluid. In principle, this process is similar to abrasive jet machining, except this is in the case water is used as a carrier fluid in the place of gas. This process offers advantage of cutting electrically non-conductivity as well as different to machine materials comparatively more rapidly and efficiently than other processes. So other advantages claimed for this process may be listed practically noticed: high cutting speed, multi-directional cutting capacity, no fire hazards, no thermal or deformation stresses, high quality of machine lids, easy adaptation for remote control, recycling of abrasive particles, lower power requirements, almost delamination and reduced fire. So water jet and the stream of abrasives coming from two different directions mix up and pass through the abrasive jet nozzle. Here, a part of momentum of water jet is transferred to the abrasives. As a result, velocity of the abrasive rises rapidly. Thus, a high velocity stream of mixture of abrasive and water impinges on the workpiece and removes material. Depending upon the type of the workpiece material being cut, material removal may occur due to erosion, shear, or failure under rapidly changing localized stress speeds. In abrasive water jet cutting, an erosive action of an abrasive laden water jet is employed for cutting, drilling, and cleaning of hard materials. Okay, so in abrasive water jet machining, there are four important elements. Okay, four important elements, that is pumping system, abrasive feed system, abrasive jet nozzle, and catcher. So these are the four important elements in abrasive water jet machine. Now we are going to study about one by one. The first one is pumping system. Okay, so pumping system, we know that the name itself indicates pump. We can transfer the one fluid to another fluid. We are using the pump. So it produces high velocity water jet by pressurizing the water as high as 415 megapascal by means of an intense sprayer. To occur with such high pressure, 75 horsepower motors may be required. So the water flow requirements up to 3 gallon per million are quite common. Okay. Then abrasive feed system. So it must deliver a controlled flow of abrasive particles to the jet nozzle. Okay. So the present abrasive feed system delivers a stream of dry abrasives to the nozzle. So flow of a water jet in a mixing tube is responsible to create enough suction for the flow of the abrasive. So flow rate of abrasive can be controlled by changing the diameter of the control orifice. So such systems have the limitation that they cannot supply the abrasive over a long distance. To overcome this drawback, researchers are developing a system in which it is possible to directly use slurry. So instead of mixing them in a nozzle, so this system would make it possible to split slurry over a long distance. However, it would require more power than the power required by the dry abrasive feed system. So highly pressurized water is passed through the nozzle of diameter ranging from 0.075 to 0.635 mm to obtain the desired velocity of 700 meter per second of a jet abrasive water mixture. For long life, we need the nozzle made of sulfur. That means that the cover maybe say we can say 250 to 500 R. So the next element is abrasive water jet nozzle. So abrasive water jet nozzle, it performs two functions. So here the first one is mixing of abrasive jet and water to form high velocity and high velocity water abrasive jet. Okay. So the two functions, what are they? Mixing of abrasive jet and water and to form a high velocity water and water abrasive jet. It should give a coherent and focused abrasive steam at exit from the nozzle, which is made up of sapphire, tungsten carbide, and boron carbide. So the internal details and two kinds of abrasive jet nozzles are shown in the diagram. So there are two abrasive jet nozzles we have using in this abrasive water jet machining. What are they? First one is single jet side feed nozzle and a multiple jet feed nozzle. So in a single jet side feed nozzle, abrasive fluid from the side mixed with water jet in the mixing chamber. The nozzle is less expansive, simple to make, but does not provide the optimal mixing efficiency and it experiences a rapid wear at the exit of the part of the nozzle. So the multiple jet center feed nozzle consists of a centrally located abrasive feed system surrounded by multiple water jets which are disposed such as a converging annulance of water is produced. It gives a higher nozzle life and a better mixing of abrasives into the water jet. However, it is very difficult and it is very cost to fabricate such nozzles because of the angle of convergence. Then the next another one final important elements in abrasive water jet machine, that is the catch. So another element of this system is catcher, which is used when the nozzle remains stationary and the workpiece moves. So catcher is a long narrow tube placed under the point of cut to capture the used jet in case when the workpiece remains stationary and the nozzle moves, a water-filled settling tank is placed directly underneath the workpiece. So high pressure water from the pump is transmitted to the nozzle by a high pressure flexible hose. When we are using the high flexible hose, the pressure is less than 124 megapascal, and if the pressure is higher than 124 megapascal, we are using the rigid tubing. Okay. So the next one is the process variable. Okay. So the process parameters. So here the process parameter is given: the water flow rate and pressure, abrasives and the water nozzle and abrasive cutting parameters, workpiece material, mixing tube, angle of cutting, transfer speed, and number of passes. We know that the process parameters play a vital role in a machining process of the abrasive jet or abrasive water jet machining. Now we are seeing one by one. So water jet pressure. So water jet pressure during slotting. So relationship between pressure and the depth of a cut for a different abrasive flow rate and the nozzle diameter. So next slide we are going to study about the diagram, the comparison. So here look at the diagram. So here it shows the effect of a water jet pressure on the depth of cut for the various suppressive flow rate, and this right hand side diagram shows the relation between the depth of cut and the water jet pressure for a two different nozzle diameter. Okay, so there is a minimum pressure, that is a critical pressure, or we call it as a threshold pressure. Below, no machining would take place. Okay, so the critical pressure exists because a minimum abrasive particle velocity is required to cut a particular material. So critical pressure is obviously different for different workpiece materials. The machine depth tends to stabilize beyond a certain value of water jet pressure. So the machine depth versus pressure relationship becomes steeper as the abrasive flow rate increases. So when you look at the diagram, you can understand. So we will look at very carefully. So as seen, increase in pressure also increase the rate of nozzle wear and cost of pump maintenance and lowers the volumetric efficiency. So water flow rate in abrasive jet machining, jet machining, where gas is used as a propelling fluid, only small mass flow rate of abrasives up to 100 gram per minute can be achieved. Okay. So here in abrasive water jet machining, water is used as a propelling fluid which enables high abrasive flow rate. So here, so rate to be achieved and makes it possible to accelerate abrasive to high velocities over 300 meter per second. So in abrasive water jet are more suitable for cutting as compared gas abrasive jet because the earlier ones are more coherent. So water flow rate is proportional to the square root pressure of and the square of diameter of the nozzle. Okay, so this is up to the water flow rate. Now we are going to study about the abrasive flow rate. Abrasive. So the machine depth is proportional in abrasive flow rate. The machine depth is proportional to the abrasive flow rate and the square of the particle velocity. Okay, so here it is given the m, it is proportional abrasive flow rate, and pp is the particle velocity. However, an increase in abrasive flow rate beyond a critical value could reduce machine depth. Why? So increase in abrasive flow rate enhances the wear rate of mixing nozzles and reduce mixing efficiency inside abrasive water jet nozzles. Okay. So the relationship between the abrasive flow rate and the depth of cut is given in the diagram. So we draw it as a graph. So before that, I want to tell there is a here the abrasive particle size. So commonly used abrasive particles is ranges from 100 to 150 grit. There is an optimum particle size for a particular workpiece. Material also for a particular mixing chamber configuration. So okay, so this is the comparison. So recently efforts have been made to quantify the effect of abrasive particle size on depth of cut. Research have shown that the optimum particle size range exists for cutting different types of material. So mesh size 60 is more effective for relatively shallow depth of cut obtained with 2 passes. So during machining of stainless steel, okay, so it was found and it was studied, and the approximate diameter of abrasive grit is measured that is S can be obtained from the different equations we have studied. Okay, so this is a comparison, the relationship between the flow rate and the depth of cut. Okay, so here for this graph they are working for the various different materials, and the velocity and the diameter and the pressure are given various nozzle for, and especially the abrasive flow rate versus the depth of cut is studied for the aluminum, stainless steel, mild steel, and the cast iron. So these are the different parameters, and what are the results they have obtained. It is plotted as a graph. Okay, so this is a abrasive material. Next one is, so abrasive material we are using the garnet, silica, and the silicon carbide are commonly used as abrasive water jet machining. Okay. So the type of abrasive to be used is determined after knowing the hardness of the workpiece of the material. Higher the hardness of the workpiece material, harder should be the abrasive to be used. So complete recycling of the abrasives here, it is not possible. So the machine depth is also affected by the abrasive feed here. Okay. So while selecting the type of abrasive for a particular application, one should consider the cost, nozzle wear rate, environment constraints, and the machining rate and the strength of these particles. Okay. So the cutting. So here, so this is the graph which tells about the abrasive flow rate and the depth of cut for the different abrasive materials. So here in this abrasive materials we are using garnet sand, silica sand, steel grit, glass grit, aluminum oxide and silicon carbide. So we are as I earlier indicated mentioned that as the higher the hardness we are using, the higher the hardness of the abrasive materials. Then the next parameter, that is the cutting parameter. In the cutting parameter, the first one is the transfer speed. So what is transfer speed? So the transfer speed at decrease in transfer rate increase the depth of the cut. So however, if one goes below a minimum critical transfer rate, there would be hardly any increase in the depth of cut. Okay, so here the diagram. Okay, so this is the transfer rate. So here this diagram shows the optimum transfer rate that exists for generation of maximum curve area. What means the maximum curve area? It's the product of the transfer rate and the depth of cut. So however, in case of mild steel, the rate of curve area generation decreases with an increase in transfer speed beyond the optimum value. Okay. Then next important parameter, the number of passes. Okay, number of passes and the standard distance. So number of passes, the multiple passes can be employed in the following two different ways that already we have studied in the introduction. That's a single water jet with the multiple passes and the multiple tandem with a single transfer. Okay. So in case of a single water jet, whole power, the quantity of abrasives are used by a single jet, while in a second case, both the available power and the abrasives are divided among the multiple jets. So the distribution of power and abrasives among them are considered a consideration for overall optimization. So multiple task cutting requires a special catching and a contaminant precautions because the initial pass cutting results in a jet backflow. Okay. Here, so here in this diagram, we can see that. Okay, so this diagram shows the relationship between the number of passes and the cumulative depth of cut. So it is also evident that the number of passes increases, the slope of the curve also increases. So increase in the slope has been attributed to the fact that the curve acts as a local mixing chamber that tends to focus the abrasive jet stream for more effective cutting. So here the greater the cumulative depth, the lower transfer rate by the effect of a standoff distance and the curve friction drag. So standoff distance is the next important parameter. Okay, so what is standoff distance? So standoff distance, an increasing standoff distance, the standoff distance I mentioned. So it is the distance between the nozzle and the workpiece. Okay, so increase in the standoff distance rapidly decreases machining depth. So this can be explained by arguing that the liquid phase of the jet breaks up into the droplets, resulting in a free abrasive particles. So here, the diagram indicates. Okay, so these free abrasive particles rebound upon the impact that leads to a shallower penetration. So there is an upper value of standard distance beyond which the process will no longer do the cutting. However, in case of a multi-pass cutting, the curve made in the earlier passes helps the jet to remain intact. So it is concluded that what we have concluded here in this, the smaller the standard distance, the deeper is cut. The smaller the standard distance, the deeper is cut. Okay, so here is the diagram. From the diagram we can we can find. So here a model to predict the depth. It has been reported that the correlation coefficient between the predicted and the experiment values for different materials, and it is found that it is greater than 0.9. So two properties, flow stress and the critical velocity, are found to be more significant parameters, okay, in a standard. The next one is visual examination. Another parameter is the visual examination. So visual examination of the process was conducted on like stained lucite and a glass work materials. Okay, so with the help of a movie camera. So visual examination is done by a movie camera, and the specific special configuration camera which have been used for the visual examination. So the mechanism of the material removal has been attributed to two modes. So cutting wear mode that occurs as a shallow angles of impact, and the deformation wear mode which occurs in the lower part of the cut at larger angles of impact. So the nature of actual penetration of abrasive water jet in solid, and so here it's been reported. Okay, so here in this diagram it shows a relationship between penetration rate and depth of cut as a function of machining time estimated from the sequence of photograph. Okay, so it is found that the number of steps are formed below the steady state in the phase at the top. The step formation take place at the jet transfers over the workpiece. Okay, so the size of the step increases with the increase in the machine depth. Okay, so these are the important parameters which should be considered in abrasive water jet machining. Okay, so it was studied and found out the result. Next, we are going to study about the process capability or the process performance. So abrasive water jet machining process has been used to cut even thick material, that means up to the range of 200 mm with a narrow curve. So width of the curve depend upon the workpiece hardness. For hard material, the curve narrows down towards the bottom, while the reverse is true in case of a soft material. Okay. So machine surfaces have not revealed the presence of any thermal or mechanical damage to them. Okay. So that's very important. Okay. So in case of machining of glass, tray cutting may result in corrosion. So these are the some of the disadvantages which are in the abrasive water jet machining. Now the applications, very important. Okay, so without the application, we don't have any process. So this process has been employed to cut a wide range of materials, including both metals, okay, especially copper and its alloys, lead, tungsten carbide, aluminum, etc. And the non-metals like we are using the non-metals, graphite, silica, glass, acrylic, concrete, etc. Okay, so for these materials, we will use this abrasive water jet machine. So the process has been applied to machine the sandwiched honeycomb structure materials currently used in the aerospace industries. So in advantage is the capability of the omnidirectional cutting having no burst. The edges of structural aluminum plates have also been successfully cut. This technique is getting acceptance as a standard tool for cutting materials in number of industries like aerospace, nuclear, oil, foundry, automotive, and construction field, and glass. So the specific advantage claimed by promoters of these techniques are economical and environmental. Okay. So abrasive water jet machining has been employed for decommissioning nuclear facilities. The optimum performance has been reported that 0.38 mm jet at 200 megapascal with an abrasive flow rate of 0.54 kilogram per minute. So it's a wonderful parameters and the wonderful performance. Okay. In some cases, this technique has proved to be economic as compared to the conventional bulk material removal method. Okay, so here the slotting is the one of the common application of abrasive water jet technique, and various steels like stainless steel, mild steel, and special alloy steel have been cut into different shapes like plate, tube, and corrugated structures. So here the curve with observed are in the range of 0.75 to 2.25 mm. So roughness of the cut surfaces varies with machine depth and the abrasive water jet cutting parameter. So it also been reported that no embedded abrasives were seen while examining the machine surface. Okay, under the scanning electron microscope, being a cold machining process, thermostals are not discussed in the machine surface. So aluminum has been cut successfully. Okay, so these are all about the abrasive water jet machining. Okay, so I hope you can better understand about the abrasive water jet machining. Thank you. Thank you.